the live
Oh, look,
lecture.
so we have
Well,
to.
it's not. It doesn't matter. It's
Now
just
we have to behave.
short. That's okay. You don't have to. Don't really have to.
Anyway, we still have 1 minute, right?
1 minute, yeah.
Oh,
I'm gonna share the screen here.
is it recorded?
It is because then it goes immediately to the website, to the YouTube website. So essentially, we actually do this.
Oh wow! Look at all these people.
So it's very nice. What I don't know how was I gonna 1 second. I guess I usually start right on time.
Oh well, right on
that
That's a very good idea. Yeah, I put that in that one.
runs. Okay, it's usually Matthias. It's usually strange that no.
Oh.
So Burkhard usually is around, so maybe he just will come in a minute. Okay, so I think we need to start. So thank you very much, everybody, to join us once again to the online SPICE and SPIN+X seminar series that I lead here together with Lieber Schmeickel, Angela Wittmann, and Karen Everso sitting now in Duisburg, in collaboration with the SPIN+X Collaborative Research Center led in Kaiserslautern by Martina Schliemann, Burkhard Hillebrands, and here in Mainz by Matthias Chloe. The talks are Zoom webinars, as you all know. Please write your questions or raise your hands to ask a question for the speaker. Typically, we do it after the talk is done. If it's something important, I can actually interrupt and ask, but for the most part, we wait until the end. And please check out the different schedules that we have. We now have a pretty fairly full schedule, even through the summer until we have a break. But also, of course, when we have overlaps with other workshops, we don't typically have one. Now, today, we just have Stuart. As I mentioned, Stuart is the type of scientist and star and superstar that just requires a first name to be known who you're talking about. He is, of course, has had more awards than I knew could exist in a lifetime here. But particularly the latest one that he's actually received, it was an APS Medal of Exceptional Achievement in Research, but the one is the Charles Stark Draper Prize of the National Academy of Engineering, which is just a month or two ago that he received that. He's, of course, the father of spintronics and hard disk drives, and responsible for the fact that we can actually have essentially all our videos saved online. And it's a very long title that I'm not even going to attempt, but he's now a director, of course, in the Max Planck in Halle. So with this, Stuart, I'm going to stop sharing here, and I'm going to ask you to please go ahead and start sharing. Yeah, perfect. And start your talk whenever you have a chance.
Okay, then, Jairo, thank you so much for your very kind introduction. And today I'd like to tell you a little bit about some of our work on chiral spin textures on the racetrack. Some of the work I'm going to discuss was carried out here at the Max Planck Institute for Microstructure Physics in Halle, and carried out by these postdocs and students that I've listed here. I think there are too many to identify individually, but I want to thank them all for their very important contributions to the work that I will discuss. And I'd also like to acknowledge we do have a support from Samsung Electronics in Seoul, and two of the scientists there have also contributed to some of this work. Here in this initial video, you can see a drone view of some of the laboratories that we built in the last 5 or 6 years since I came to Max Planck a few years ago. And we have now a complete set of equipment to, in particular, build structures from atomic layers in different forms, and to explore how their interfaces can influence their properties. In particular, when we look at their optical, magnetic, and transport properties over a wide range of temperature and magnetic field. Today, I'm going to talk about these topics. I want to briefly introduce you to chiral spin textures. I think many of you are familiar with these, and I want to briefly remind you about what is racetrack memory. It's the concept that we can encode data in movable chiral domain walls, and I believe this memory will be the third spintronic technology that could play a very important role in the digital world of today. I then want to briefly introduce superconducting spintronics and discuss in particular some of our own work on a non-reciprocal Josephson diode effect and the possibility of using triplet currents to manipulate chiral spin textures, which is the basis for what we are building, a cryogenic racetrack memory. I'm not really going to say much about this, but I think it's very interesting to explore the possibilities of building memory and logic technologies that can work at ultra-low temperatures and can support quantum computing systems. So much of the focus in quantum computing on the qubits themselves, whether they're superconducting or whether they're spin, but at the same time, you will be needed to create electronics that can operate at these same low temperatures in order to make a complete quantum computing system. And here are some of the papers we published in the last couple of years about some of the work that I will discuss, and some of it is unpublished. So I want to just go back briefly to basics. And if you look at magnetic domain walls, in particular in materials with large unidirectional anisotropy, and in thin films, this is often a perpendicular magnetic anisotropy, then the magnetic moments in a ferromagnetic system are coupled through a Heisenberg exchange. And yet, at the same time, there can be domains and domain walls. And the domain walls have a characteristic length scale, which is determined by competition between the Heisenberg exchange and the anisotropy. And when you have typical thin film heterostructures that I'm going to introduce, in particular formed from ultra-thin layers of cobalt and nickel, the interfaces give rise to a significant perpendicular magnetic anisotropy, so that the typical length scale, or the width of such a domain, would be of the order of 5 nanometers. And this means, in particular for Racetrack, we can imagine building structures with 5 nanometer wide domain walls spaced by a few nanometers apart. And I want to show you that essentially we've accomplished that in some of our recent unpublished work. However, if we move from a one-dimensional system or one-dimensional domain wall, then in a two-dimensional system, there can be, in addition, more interesting interactions. So first, let me talk about domain walls. And in a one-dimensional system with one-dimensional domain walls, then the domain walls themselves, in which the magnetization rotates from up to down, can rotate from up to down in a chiral fashion. And shown here some very nice work from more than 10 years ago from Fudan University, where this group showed, using spin-polarized low-energy electron microscopy, that even a simple sandwich formed from a few atomic layers of iron and nickel, when placed on copper, you form domain walls which have a chiral structure. And as you can see in this cartoon, this means that when, for example, iron and nickel are placed sequentially onto copper, in this case a single crystal, the magnetization rotates from an up to a down direction, and the magnetization, as you can see, will point in this blue direction to the right. The magnetization, when it rotates from down to up, the magnetization in the middle of what is a nail wall will be pointing to the left. So in this case, the magnetization rotates in a plane perpendicular to the wall itself. On the other hand, if you reverse the sequence of nickel and iron layers, so the iron is grown first on copper, what this group found was that the chirality of the domain walls would change. This is a beautiful demonstration that interfaces in particular can give rise to a new form of an exchange interaction that is of a vector type. And this means that it directs the magnetization so that the magnetizations of neighboring moments want to be orthogonal to one another through this so-called Dirizinski-Maria exchange interaction, which is shown on the top left. And this leads to, in the simplest system, as shown here, the magnetization will, in this cubic system, would this Dirizinski-Maria interaction will be the same, let's say, in all directions. But in systems, depending upon the crystal symmetry, the DMI interaction can have different forms, and the components can be different in different directions. Nevertheless, this can give rise, in this particular case, to domain walls which are chiral with a nail structure. And chirality is super important when we consider the motion under spin-orbit torques of these domain walls. If we now go from what was essentially a one-dimensional system of striped domains in a perpendicularly magnetized system rather to a two-dimensional bulk crystals, then in those systems, the Dirizinski-Maria exchange interaction can exist, and it's typically in systems which have strong spin-orbit coupling. And in this case, you can see in this cartoon, it can lead to what is called a skyrmion. And in the so-called B20 system, which is a cubic chiral system, then the the nature of the domain walls. And in this cartoon, it shows how the magnetization rotates from the up blue direction on the outside, the periphery of this circular nanostructure, to a down direction in the middle, the red moment in the middle. You can see now the magnetization is rotating so that the moments are perpendicular to the radius, if you like, parallel to the domain wall, in contrast to the nail type domain wall, which I just introduced in the previous foil. This is a very interesting object, which is found in systems that, as I said, with strong unidirectional anisotropy, typically in tetragonal or hexagonal systems, low symmetry systems. And this DMI vector gives rise to lowering the energy when you form these boundaries with this chiral structure. So in these systems, you can find these skyrmions in some range of temperature and field, because the domain wall itself lowers the energy through the DMI interaction. This leads then to the field of non-collinear spin textures. So on the left-hand side is the object I just showed you, the block skyrmion, and it has a close partner, the nail skyrmion, shown on the right-hand side, which is the two-dimensional equivalent of the one-dimensional domain wall introduced 2 foils ago. And in this case, the magnetization rotates from up on the periphery to down in the middle by rotating with the moments in the wall being along the radius rather than along the circumference, as in the block skyrmion. So a few years ago, it was predicted that there could be, in addition to these two objects, something called an antiskyrmion, and this will arise in systems with certain symmetries such that the DMI vector will have different signs and magnitudes in different directions in the crystal structure. And in particular, in certain symmetries, certain crystal structures with a certain so-called D2D symmetry, then the periphery of this object will now consist of portions of nail walls and portions of block walls. And as you go around the periphery, you can see the black dotted line corresponds to the nail wall, and the red one corresponds to, oh, well, it's the opposite. The red one is the nail wall, and the black dotted line is the block wall. And as you rotate, you can see you go from a black dotted line to a red dotted line, black to black, and the wall changes from nail to block to nail, and it changes actually its chirality as it does this. This is the objects you find in certain systems, again, depending upon their crystal symmetry, typically with strong spin-orbit coupling. Typically, in addition to these two-dimensional objects, or they can be three-dimensional in the case of the block skyrmions, nail skyrmions, then there can be a one-dimensional helical or cycloidal structure shown underneath these objects, where in one direction there is a rotation of the plane of magnetization in either a cycloidal or helical fashion. And this is, and in the case of the antiskyrmion, then again along different directions you get these different types of objects. So we and others image these objects using in particular Lorentz transmission electron microscopy. In this case, we take a single crystal and we use focused ion beam milling to mill out a lamellar thin sheet, which is sufficiently thin that an electron beam can be transported through that thin lamella. And so we need a beam energy, in our case, of 200,000 volts. And then we place this lamella in the electron beam, and as the electron beam passes through that lamella, through Lorentz forces derived from in-plane components of the magnetization, the electron beam will be deflected, and this allows us to determine what type of texture we have. And in particular, you can see then that we show below in the bottom, this is the image we expect to see in this Lorentz microscope, depending upon whether we have a block antiskyrmion or a nail skyrmion. And these are actually calculations by Changping Ma, who is a PhD student and then postdoc. Now he's back in China. And he first used micromagnetic simulations to calculate these spin textures, and then used standard transport intensity equations to derive these Lorentz forces and therefore the image in the imaging plane of the microscope. And what's interesting is that the block skyrmion looks like a single bubble of increased intensity of the electron beam, whereas in the nail skyrmion, the deflection of the electron beam is around the circumference of the object, so that there's no, actually you see nothing in plain view. If you tilt the object in the nail case, you can actually see something. I'm going to come back to that later. And in the antiskyrmion, we calculated we should see this clover leaf-like structure with two regions of increased intensity here shown to the top and bottom, and two regions of decreased electron intensity to the left and the right. And indeed, after considerable efforts, we could see this. This is a work originally by Ajay Nayak, who was a postdoc in my group. And these are some beautiful single crystals of this material. It's a Heusler compound, which is normally manganese 2 platinum tin, but to create a stable structure, there are manganese deficiencies, and in this case, some of the platinum was replaced with palladium, about 10%. These crystals are made by in Claudia Felser's group in Dresden, and we took crystals from Claudia and made these thin lamella and imaged them in our Lorentz microscope. And we could see for the first time shown in a antiskyrmion. And you can see it clearly looks like this predicted clover leaf-like structure. And as in the microscope, we can vary the temperature and the magnetic field. These are actually at room temperature. And you can see that the antiskyrmions typically form hexagonal arrays of these objects, is shown on the top. And then as we further increase the magnetic field, then out of the plane of this lamella, then you can see that there's not much change in the array of the antiskyrmions, except eventually they will disappear at high enough magnetic fields, which is shown in the bottom right, with just a single chain of antiskyrmions along the edge of the lamella. We can use a different technique for imaging these objects. This is variable temperature magnetic force microscopy, in which case we're no longer probing the in-plane components, but rather the outer plane components. And in this case, we've also, instead of making a lamella with a uniform thickness, we've made a lamella whose thickness varies from the left, 630 nanometers, to the right, 4.2 microns. So these are no longer electron transparent. And the reason for exploring this thickness range was to try to understand why the size of the skyrmions, and in this case, the one-dimensional helical structure, the period of that structure, evolves with thickness. And you can see here very nicely, if you look at C, then this is a magnetic force microscopy image again of the outer plane components now. And you see the outer plane component is rotating from an up to a down direction. This is shown in a line through this image in E, and you can see very, very clearly the magnetization and is rotating from up to down with a period that is increasing substantially as the thickness of the wedge is increased from the left to the right. And the images C, B, and D are simply obtained by applying a large magnetic field in different directions to the surface of this lamella. And when you reduce the field to 0 or to some finite value, you see these different one-dimensional structures. These are actually all in 0 magnetic field. And what we found then on the right-hand side, you can see that the wavelength of this helical structure increases systematically as the thickness of the lamella in which we're imaging these objects is increasing by more than a factor of 10, from 100 nanometers for the thinnest layers, where we could use Lorentz microscopy, to more than a micron for the 4-micron thick layers. And these are giant objects, more than 1 micron in size, that we can then detect optically as well. Now, if we now apply a magnetic field to this object out of the plane, then the helical structure shown in A evolves into the antiskyrmions. And the antiskyrmions in this magnetic force microscope look like these little circular dots, where we're just looking at the component of magnetization in the interior of these antiskyrmions. And again, you can see visually that the diameter of these antiskyrmions increases from left to right in each of these lamella as the lamellar thickness is increasing. And on the right-hand side, you can see we plotted the diameter of the antiskyrmion as a function of the lamellar thickness at room temperature. And again, you can see a factor of 10 change in the diameter. And in fact, the diameter of the skyrmions is the same as the wavelength of the one-dimensional helical structure. So the reason for this dramatic variation in thickness we showed was due to the influence of dipole-dipole fields, which are more important the thinner is the lamella, and it actually causes a shrinkage of the size from that expected from the strength of the DMI and the Heisenberg exchange. Normally, the size of these objects is determined by the ratio of the DMI to the Heisenberg. So in this case, it turns out that the dipole field suppresses the size by nearly an order of magnitude. So it's the dipole interactions play a very important role in this particular case. And indeed, dipole interactions are always important in magnetic nanostructures on the nanoscopic scale. So it turns out these dipole fields play another important role in that they can allow for a different type of structure in the same Heusler compound, the same manganese 1.4 platinum tin compound. Or Jagannath Yener, a student, now he's a postdoc in America, he found that surprisingly, he could see another object, another non-collinear spin texture that had not been predicted, and was a surprise because I haven't really discussed, but the skyrmionic objects are of interest because they're topological. There's some topological charge associated with them that's believed to prevent them from evolving from one structure into another. However, what Jagannath found was in the same material, depending upon the temperature, you could achieve a totally different structure which had never been seen before. And it turns out it's a block skyrmion, but it's no longer circular in shape. It has this elliptical shape that you can see very, very clearly in these beautiful Lorentz micrographs that Jagannath took. And here you can see again, how they evolve in magnetic field. And in the bottom right, you can see how these elliptical block skyrmions evolve from the helical one-dimensional structure, which is stabilized at different magnetic fields. And the reason for forming these structures is these objects have the elliptical objects, which, by the way, the long axis of the ellipse is only formed along of one of two perpendicular crystallographic directions. And along those directions, as I mentioned at the very beginning, they're the directions that favor a block type wall, and the block type walls themselves have a lower magnetostatic energy than the Néel walls. This is why they're formed. And so we found these objects, and it turns out by varying the temperature, we can switch from antiskyrmions to these block skyrmions, or at the same temperature, we can see both. I don't want to say too much more about these objects, but we found a rich physics in basically one compound, this manganese 2 platinum tin Heusler compound. We've seen the coexistence of skyrmions. Of course, we found antiskyrmions for the first time. We proposed we could use these spin textures on the racetrack that I'm going to discuss to store information. You could store zeros and ones in different topological spin textures, the elliptical skyrmion, antiskyrmion, elliptical skyrmion, and the antiskyrmion. We also observed for the first time fractional antiskyrmions, which were unexpected at the edges of devices through a bulk boundary correspondence. And we've explored, Jagannath has explored extensively the dynamics of how you can evolve from one type of spin texture to another, and looked at the topological phase transformations in that regard. So a rich, very rich material. So now why are we interested in these objects? We're interested mostly because we want to build a magnetic racetrack memory. And let me just remind you what that is. I've been working on this now for more than 20 years, since I first proposed this concept in 2002. It's a long time ago. And the concept was, as shown on the right-hand side, we would build a vertical homogeneous magnetic nanowire in which we would magnetize the wire in one direction or another direction, in these blue and red directions, and we would encode digital information as the domain walls, the walls between the blue and red regions, which I said at the beginning can be nanoscopic if you design the material properly. And the idea is that the presence or absence of this domain wall would be a 0 or a 1. And furthermore, by passing current pulses into this racetrack, we can move all the domain walls synchronously in the same direction, backwards and forwards, and bring these walls to elements that would be designed to read, and that would be designed to write the domain walls into the racetrack. So this is what I proposed. And I said, look, this is non-volatile, could have very high density, could be very, very fast, and could enable us to replace the magnetic disk drive that today uses a spintronics sensor that I invented many, many years ago. and magnetic disk drives store 70% of all digital data today. Maybe we could replace it with a racetrack, which is non-volatile, non-mechanical, and therefore more reliable and would be much faster. So this is what the proposal was. And over the last 20 years, we've evolved the racetrack materials from initially in-plane magnetized racetracks formed from nickel iron cobalt alloys, which are known to have very, very large spin polarization of the current through spin-dependent scattering. When you pass current into that material, then the current itself could, through that spin polarization, carry spin angular momentum and cause the domain walls to move. And that's what we demonstrated in this paper in Science in 2008, in which we could, with current pulses, move a series of domain walls backwards and forwards within a racetrack formed from a nickel iron cobalt alloy. However, those types of materials have no anisotropy, so the domain walls are very large, hundreds of nanometers, and indeed they're highly flexible. They can extend over microns. So this is not good. So we switched to instead multi-layers formed from cobalt and nickel. And those multi-layers, the interfaces, give rise to a strong perpendicular magnetic anisotropy. So these shrink the domain walls, and we demonstrated that we could move these domain walls very similarly as in the cobalt-nickel alloys, at roughly the same speed, about 100 meters per second, for useful current densities. So in the version 3.0, we built the racetrack, the perpendicularly magnetized racetrack, on top of a layer of platinum, and it had been shown by others that this platinum gives rise to a strong spin. Well, we actually demonstrated strong spin Hall effect that moves the domain walls at much higher speeds, about 3 times higher than in these versions 1 and 2, about 300 meters per second. And this is because in the platinum layer shown as yellow, the current is transformed into a orthogonal transverse spin current that diffuses into these magnetic layers and causes them to move at high speed. It only works because at the same time that platinum underlayer gives rise to a Delizinski-Maria exchange interaction that makes the domain walls chiral. And so it's the only reason why all the domain walls move in the same direction is this chirality. The chirality influences the direction in which the domain walls move for the same transverse spin current. This is the only reason why they move in the same direction. That's something we demonstrated and proposed. Finally, in version 4.0, which is the most interesting one, we demonstrated that in a synthetic antiferromagnetic racetrack, there is another torque that moves the domain walls at even more efficiently. We called it an exchange or giant exchange coupling torque. And this is a result of forming this structure, which consists of 2 racetracks, 2 copies, one on top of each other, which are coupled through an ultra-thin layer shown here as this gray layer of typically ruthenium, it could be something else, which gives rise to a strong antiferromagnetic coupling. Again, this is something that I showed, well, a long time ago, 30 years ago, and I demonstrated, even at that time, I proposed and using a synthetic antiferromagnet to eliminate the dipole fields, which I already showed you are so important, and which would otherwise give rise to interactions between the domain walls, as shown in these cartoons for the versions 1, 2, and 3. They are so large, these fringing fields on the nanoscopic scale cause interactions between the walls within and between neighboring racetracks. However, the synthetic antiferromagnetic racetrack, we eliminate the dipole fields because, as you can see in this cartoon, a red region pointing down in the upper racetrack is exactly on top of a blue region pointing up in the lower racetrack. So we can design the net magnetization everywhere to be 0, and that there to be effectively no long-range dipole fields. Very important. And it turns out that we discovered that this antiferromagnetic coupling field itself gives rise to this giant exchange coupling torque, only possible in these synthetic antiferromagnets. So then the domain walls move several times faster at speeds of about 1 kilometer per second. Very fast, and that's fast enough to make very, very interesting racetracks. In fact, you probably don't want the walls to move much faster. So this is fantastic and makes basically racetrack possible. So all our work for all those years, a lot of our work was using optical techniques to measure the domain walls. So here you can see a typical structure. It consists of in this case, 3 angstroms of cobalt, 7 angstroms nickel, 3 angstroms cobalt. So it's a very, very thin magnetic layer. It's grown. The black layer here will be platinum. And we have some other layers to optimize the growth and to prevent oxidation. In this particular case, this is just a simple ferromagnetic racetrack. And we explore the motion by, as you can see on the right-hand side, using Kerr microscopy, which is, of course, an imaging technique where we look at the reflection of polarized planes of light, and it's deflected to the left or to the right in reflection, whether we have up or down magnetization. And this is shown then in a sequence. Let's say at the bottom, you can see 1700 nanometer wide racetracks, and we're showing an image of a single domain wall where the magnetization is black is up and gray is down. And then we apply current pulse, and the domain wall moves along the racetrack. We take another image, and by taking a series of images in the Kerr microscope after applying one or more current pulses, the domain walls move, and we can determine their velocity. And in this case, what we've done is we shrunk the width of the racetrack from 1700 to 14 to 1100 to 800 to 500 to 200 nanometers. We can still see the domain walls in 200 nanometer wide racetracks, even though the wavelength of light is much larger. And then we could use this to determine the velocity. This is the velocity of the domain walls shown in the 2 leftmost pictures as a function of the current density within nanosecond long current pulses. And you can see essentially the velocity versus the current density is pretty much unchanged as we change the width by considerably from 1700 to 200 nanometers. Now, what happens is the threshold current to move the domain walls, which you can see is about 5 times 10 to the 11 amps per square meter, does increase a little bit as we reduce the width, but not much. So this was quite a surprise to us that the threshold current to move the domain walls, which is really determined by inhomogeneities within the layers themselves, would be so little affected by this dramatic reduction in the width of the domain walls. So this is as far as we can go optically. And so we can, I just wanted to say I want to move then to electrical detection, but just to remind you, we also can imagine new materials that can allow for reductions in this threshold current density. Originally, when we started working with Samsung, we wanted to imagine Racetrack as a replacement for flash memory. And it turns out then you don't need the domain walls to move very fast, but you need low current threshold current densities. And we were able to reduce the current density by almost a factor of 10 by changing the underlayer materials to a new set of materials. These are formed from a iridium aluminum, roughly 50-50 alloy, which forms an atomically arrangement, layers of iridium, layers of aluminum, one on top of each other, even at room temperature. And this material we demonstrated has a huge spin Hall effect, the conversion of current to spin, which is many, many times higher than in platinum, the typical material. This leads to the significant reduction in the strength of the threshold current to move the domain walls, as shown in this image in the bottom, in the middle. And then we can then show that we could move domain walls backwards and forwards very effectively in this new class of materials formed from iridium and aluminum, but it turns out is a very large class of materials with the so-called L10 structure, which give rise to huge spin Hall effects from extrinsic means, plus also gives rise to long-range oscillatory interlayer coupling, as we've demonstrated. But now if we switch to a different technique for measuring the motion of the domain walls, now we look at domain walls where we're detecting them using the anomalous Hall effect. So when you pass a current through a magnetic material, you will see a different Hall effect, which is due to a spin-dependent transverse voltage caused by spin-dependent scattering of the electrons from the magnetic moments, typically. And what does it mean? Now we build, as you can see in the bottom left in this SEM, we build a racetrack where the racetrack is only 73 nanometers wide, and that's that structure you can see, which is built on top of an arrangement of platinum electrodes. So basically here, we made our structure platinum, cobalt, nickel, cobalt, ruthenium, cobalt, nickel, cobalt. And then we've used electron beam lithography to pattern all the way through the magnetic layers, all the way through to the platinum. And then we've made the platinum to be the electrodes we need, the transverse electrodes, to measure the transverse Hall effect. And at the same time, there's a wing of platinum extending beyond the racetrack. And this wing, depending on how you engineer it, allows us to measure the position of domain walls, which are up to 20 times as far from the Hall sensor as the width of the Hall sensor, as the width of that wing. So this is really interesting as a means of detecting domain walls anywhere in the racetrack. So we can have multiple Hall sensors or just one, or we measure up to 16 in our experiments as shown in the top left. What we do now, the top left shows you optical images of as we move a single domain wall through the racetrack, and in the top middle you can see the anomalous force signal as we apply. The iteration number is the number of current pulses that we apply, and on the top you can see the voltage changes from +9 all the way to +16 volts, so that the intensity of the current we're passing into the racetrack significantly increases, and that means you need a smaller number of current pulses to move a single domain wall from the left to the right of the racetrack. And when, of course, we reverse the current, the domain wall will move backwards. And you can see that the single domain wall moves effectively pretty uniformly along the racetrack, backwards and forwards, without any significant trapping of that domain wall. This allows us then to position, using these nanosecond long current pulses, the domain wall anywhere along the racetrack. And we've just shown in the bottom middle, you can see we positioned the domain wall at one of 4 distinct sites. And on the bottom right, you can see that we can do this many, many times, and we can see that we can position a single domain wall to a positional accuracy of about 30 nanometers, and we can certainly space them apart better than 100 nanometers. So this is a very important step towards a fully fledged racetrack memory. So this is very exciting. We've now gone from micron-sized racetracks to 73 nanometer wide racetracks in which we can move domain walls effectively, equally efficiently, but we can now position them using this anomalous Hall signal to positions of with an accuracy of a few tens of nanometers. This is very close to what we would need to build a super dense racetrack memory. I want to just mention one other final point without going into any details. I mentioned earlier that the racetrack, we need a reading element, so we can build into the racetrack a reading element, which is a magnetic tunneling junction. We essentially have a reference magnetic electrode formed from a synthetic antiferromagnetic layer itself, which is above the racetrack, separated by a thin magnesium oxide tunnel barrier layer. So now as the domain wall moves, in this case from the left to the right, underneath this reference electrode that forms the tunnel junction, of course, the signal will change. So in this case, we have a change in resistance of this integrated tunnel junction of about 100%. So it's very easy to detect the domain wall. What we want to do now is build a single domain wall racetrack, where shown in the cartoon on the right-hand side, we switch the domain wall by applying a 500 picosecond long current pulse, and the domain wall is switched from the left side of the middle tunnel junction to the right side. Basically, the rest of the structure, these large triangular regions, are just for electrodes to detect the domain wall through the tunnel junction resistance. And so this is the first time that ultrafast writing of a domain wall has been demonstrated with ultra low energy, and demonstrates the possible use of a single domain wall racetrack as a replacement for the fastest memory today, which is a static random access memory. Those memories typically occupy 50% of a chip today and take a lot of area in the silicon. If we could replace them with a single domain wall racetrack, we would use up much less area, and moreover, it would be non-volatile. So this would give a huge advantage. So we think this could be the very first application of racetrack. Certainly easier to build a single domain wall racetrack than a multi-domain wall racetrack. I just wanted then a couple more points to make while we still have some time. One is I mentioned three-dimensional racetracks. And so in my group, we have several projects to build three-dimensional racetracks. One of them is this very nice technique. This is by Kei-Gu, who's a PhD student in my group. And he used a technique that was originally developed, in particular, the material we're using by Harold Wang at Stanford University, who showed that this strontium-3 aluminum-206 SaO, it's an oxide which is water-soluble. So we grow this water-soluble oxide by pulsed laser deposition onto a substrate. And then on top of that SaO, we grow our racetrack. And it can be a simple ferromagnetic racetrack or a more complicated SAF racetrack, as shown on the right-hand side, these blue layers. You can see it's platinum, copper, nickel, cobalt, or a SAF, synthetic antiferromagnetic racetrack formed from the same platinum, cobalt, nickel, cobalt, twice with ruthenium in between. So what does Kei-Gu do? He developed this technique, which is non-trivial, to dissolve the strontium-3 aluminum-206 from the edges of a 1 centimeter by 1 centimeter wafer. And then he takes the membrane that is so formed, which is the racetrack, on a magnesium oxide layer, like an underlayer. He takes that and on water and then transfers it via water onto another base. And the base here, shown in this cartoon in the bottom, is a pre-patterned sapphire substrate where he's made these hillocks up to 1 micron tall. And then he basically transfers the membrane, which is now very flexible, and the membrane follows the underlying pre-patterned substrate. And he could see the domain walls moving in this initially three-dimensional structure. What this is shown here on the left in E, you can see a cross-section TM of the 3D racetrack. You see that black line. It's only a few nanometers thick, and it almost nearly follows the sapphire substrate, but almost nearly follows. And that's what we see. And we can then pass domain walls into this racetrack. And what Kei-Gu found was that if you take the SAF racetrack on the right-hand side, you can see the similar velocity versus current density. This is the current density in nanosecond long pulses as the domain wall is moved over these protrusions up to nearly 1 micron tall. So this is amazing. Here they're moving at speeds of nearly 700 meters per second, so very fast. And this is then, if you like, first three-dimensional racetrack. It's a proof of principle that we could build a three-dimensional racetrack in this way. Another project, which again, I don't really have too much time to discuss, is where we introduce a geometrical torsion into a racetrack. This is more for understanding the competition between spatial chirality, if you like, and the spin chirality within the domain walls. So here, this is a project again by another PhD student, Andre Farina. And what he did, he built a three-dimensional printing system using multiphoton lithography and using super resolution techniques. So he could introduce a polymer into the microscope and cause polymerization and therefore form a structure with a pixel size of about 50 nanometers, which is many times better than any commercially available lithography printing system. And so, as you can see in these photographs of or SEMs of the structures that Andre has built, we build structures which are like little bridges, if you like, with flat surfaces, no torsion, or where the surface has a torsion twisting to the right and then twisting to the left. And then on top of this polymerized structure, which turns out has a smooth surface, Andre was able to sputter deposit the racetrack materials and then observe the motion of domain walls. And what you find then is that depending upon whether you have torsion or whether the torsion is clockwise or anti-clockwise, then sequence of domain walls with up, down, which are red, and down, up, blue, will move at different velocities. And it turns out this is due to the geometrical torsion that we've introduced and its impact on the chiral domain wall. So this is a very nice demonstration of the interaction of spatial and spin chiralities. We're still working on getting this published. So in the last few moments, I want to kind of switch topic, but come back to Racetrack in a moment. And this is the very interesting field of superconducting spintronics. And in particular, the possibility of creating new forms of superconducting materials in which the supercurrent is carried not by conventional Cooper pairs, in which you have a pair of electrons with opposite spin and opposite momentum, but the electrons have spins which are parallel to one another. And this is a very interesting concept. And the basic idea is that if you take a conventional superconductor shown as S, and you form an interface with a ferromagnetic material, then typically the exchange field in the ferromagnet will quench the superconductivity because the superconducting Cooper pairs want to have their spins antiparallel. However, there's a possibility of forming in the ferromagnet no longer conventional Cooper pairs, which are spin singlet, but spin triplet pairs. And the reason for this, if you look at the energy band diagram in a cartoon fashion, the energy versus momentum of the spin up, shown in red, and the spin down band, shown in blue, then they exchange split, as in all ferromagnets. And this means that the Fermi energy, the spin down and spin up electrons will have distinct K vectors. So now when you form a Cooper pair, then the K vectors will be a finite K component. And it turns out this is originally work by Busdin in 1982. He showed that you form now a superconducting condensate by proximity in the ferromagnet with both a spin singlet and a spin triplet component, which oscillate in magnitude out of phase with each other, as you can see in this cartoon shown on the bottom right. So it's a very interesting concept that superconductor by proximity to a ferromagnet can create triplet pairs. And this is a different report. This is Eschrig, where we've basically taken this cartoon. It's not a cartoon. This is from his review. And you can see then the green is a singlet component of the superconductivity, and the red is the triplet component. So you see that's what happens. But the two components decay quickly in the case of a conventional ferromagnet. It depends, of course, on the degree of polarization of these electronic bands in the ferromagnet as to the extent, the distance of which you find the decay. So this is just to show you here, student Ivan Kindiak, PhD student here, and Swapna Mishra, a postdoc, have essentially replicated some data from the Leiden group of Jan Arts. And what they've shown is in a vertical Josephson junction, with superconducting layers formed from a conventional niobium shown in blue, then between the top and bottom electrodes shown in blue, they place a magnetic layer shown in red. The magnetic layer here is formed from the same material as in our racetrack, cobalt-nickel multilayers, which are perpendicularly magnetized. And then what they do is they look at so first, very interestingly, that red layer becomes essentially superconducting, and we can pass a supercurrent from the top to the bottom niobium electrodes. However, that ferromagnetic layer will quench the superconductivity. So now we can measure that by the critical current at which the superconductivity is suppressed. And this critical current shown in the black, the singlet structure shown like this, will decrease quickly with the thickness of that perpendicularly magnetized structure shown on the left-hand side. On the right-hand side, shown in orange, is what we call a triplet structure, in which we add more magnetic material, in this case, in-plane magnetized nickel. So it's thicker, 1.2 nanometers, so that's now in plane. And now you have a structure in which you have a non-collinear magnetic structure, two layers, the bright red nickel in plane and the darker red nickel cobalt out of plane, which are orthogonal to one another. And this was predicted by Sébastien Bergeret in this PhysRev letter in 2001, that such a non-collinear spin texture allows for the propagation of triplet pairs over much longer distances. And you can see on the left-hand side in the orange dots that indeed the critical current is hardly changed as the PMA thickness is doubled, and as compared to the singlet structure. So the concept of this non-collinear spin texture stabilizing triplet superconductivity is a very interesting one. It's been observed now over the last 20 years in a number of different systems. But we actually explored it in an intrinsic non-collinear system, which is a chiral antiferromagnet, which we've been exploring for a number of years. This is the system manganese-3 tin and manganese-3 germanium. In this system here, you can see in a single layer, you form these triangles of manganese atoms separated by tin atoms. It's a Kagome lattice. And because of frustration, the manganese atoms have their moments oriented at 120 degrees to each other. And because of the weak de-Leszczynski-Meria term from the tin component, this leads to actually a chiral triangular structure. Very interesting structure. There's also weak anisotropy favoring magnetization on the manganese atoms pointing towards the tin. This leads to a slightly small net magnetic moment with which you can manipulate the structure into a single antiferromagnetic domain state. And it was predicted by two groups, by Alan McDonald's group and Claudia Felser and Jürgen Kubler, that these types of systems should display large anomalous Hall effects. In other words, look like a ferromagnet. I don't want to discuss this in detail. We've been exploring, in particular, how we could switch the antiferromagnetic state using spin orbit torques, and we've demonstrated that it's dominated by heating. Nevertheless, we can switch the state to a great extent in these materials using spin orbit torques, but only when there's a lot of heating. We don't care about that. I just want to point out that we explored the possibility that this non-collinear spin texture, which Bergeret had predicted is needed for long-range triplet supercurrents to propagate. So this is some work by Kunrock, John, a postdoc in my group. Now he's back in Korea. And what he was able to show was you could form a Josephson junction between these two blue layers shown here, which we used electron beam lithography to create on top of this green layer, which is this chiral antiferromagnetic structure. And what he found was long-range supercurrents would flow from one blue niobium electrode to the other, even though this system has manganese atoms with huge magnetic moments. A lot of magnetization, but it's in a chiral non-collinear structure. And this, we demonstrated, stabilizes long-range supercurrents consistent with long-range spin triplet superconductivity. We think this is a very exciting possibility, and it's basically for the reasons I discussed earlier, based on these predictions of Bustin and Bergeret and others. How do we see this? Then we look basically at the current flowing between those two niobium electrodes through manganese-3 germanium for different separations of those electrodes. And the current, let's say, shown in A on the vertical axis as a function of the voltage, shown on the x-axis, the voltage is 0, but current is flowing, and the current flows until you exceed a certain critical current, and then the system becomes normal. And that critical current for superconductivity will, of course, decrease with temperature, and it will also decrease with increasing separation of these niobium electrodes. Nevertheless, we showed, or Kunrock showed, that we could see these supercurrents flowing over very large distances with a characteristic length of more than 150 nanometers. 150 nanometers, that's the decay length. So it's a very long distance. Well, I just want to, in the last moment, discuss the one other effect that we have discovered in a whole range of systems now. This is the first work on a 2D Van der Waals non-magnetic system nickel ditelluride. So it's non-magnetic and has a symmetric crystal structure with a center of symmetry. In principle, this breaks neither time reversal nor inversion symmetry. However, it's a very special material with a Dirac semi-metal, and it has spin-polarized topological surface states. This is the reason why Benabir Powell, postdoc in my group, explored this system. And what did he do? He made junctions, Josephson junctions, just like the junctions I showed you with the chiral antiferromagnet. They were made with thin films. Here we exfoliate a flake shown on the left-hand side in this image. You can see the flake, this irregularly shaped object, formed from a thin layer of nickel ditelluride, exfoliated from a single crystal. And then the orange lines are conducting lines of niobium formed by electron beam lithographic techniques separated by 120, 350, and 580 nanometers, all on the same flake. And what Benabir showed was that as you reduce the temperature, then you see first a resistance drop when you measure the resistance between the two adjacent niobium electrodes as the niobium becomes superconducting, and then you see the nickel ditelluride itself becoming superconducting at a lower temperature, and that lower temperature will drop with increasing separation. But you see these are enormous separations between these niobium electrodes, and on the right-hand side, you can now see the voltage between those two niobium electrodes as a function of current, and you can measure the critical current for superconductivity. And in this case, in the absence of any external magnetic field, the critical current for current flowing to the left and to the right are the same. But you can see the critical current decreases with increasing separation. And now, subsequent to this published work, we've seen supercurrents flowing over more than a micron spacing between these electrodes. These are enormous distances. So why is this interesting? Turns out that when we apply a small in-plane magnetic field, this here is 20 millitesla, perpendicular to the supercurrent, then we see this extraordinary result that the critical current for superconductivity, when the critical current flows to the right, the plus direction, is much smaller than when it flows to the left. So we see this huge asymmetry in the critical currents for superconductivity. This has only recently been observed as a superconducting diode effect, originally by Taro Ono just 3 or 4 years ago in a tricolor superlattice. This is totally different, and the origin here is totally different. What it means is, as shown on the right-hand side, you can see that when the current flows in one direction, which is the blue, switching from minus 25 to plus 25 microamps, the voltage only appears for the current flowing in one direction. For the other direction, the voltage is 0 because it's a supercurrent. So it's normal in one direction, superconducting in the other direction. So it's a very interesting non-reciprocal effect. And we think we understand this pretty well in a collaboration with Liang Fu and his group at MIT. We showed this was due to finite momentum Cooper pairing that I mentioned earlier. But here, it's due to the spin polarization of these surface states. And interestingly, if we look at the asymmetry in the critical currents for left and right flowing current, as shown in the top left, without any magnetic field, it's 0. The asymmetry increases to 60% here for a current for a field of a few millitesla, but with further increase in field, it decreases. It changes sign and then will continue to oscillate. And this oscillation is due to the oscillatory nature of the phase difference between the two niobium electrodes. And this is due to, we think, second order Cooper pair tunneling. And we can explain then this field dependence in this way, and in particular, the temperature dependence, which in this case, as you reduce the temperature away from the ordering temperature of the nickel ditelluride, increases in this fashion, increases as a product quadratically with the change as the temperature is further removed, further decreased. Well, these results, experiment and theory work very well, so we believe we understand the origin here as due to finite momentum Cooper pairing, similar to the result for a ferromagnetic superconducting interface. So why are we interested? Since I'm nearly running out of time, I'm going to tell you why we're interested in building a cryogenic racetrack memory. And the idea would be, okay, we could include into the racetrack this Josephson diode, and it would be a very interesting reading device, because in one direction, one magnetization direction, we would see a signal, and the opposite magnetization direction, we see no signal because of the superconductivity. And so we would integrate this reading Josephson diode into the racetrack. Now, I earlier mentioned the racetrack was formed in particular from platinum and cobalt, nickel, cobalt. So recently, we've observed that we can make platinum superconducting by proximity to niobium, and we see a diode effect even in platinum. So we think this is the most exciting possibility of building diodes directly into the racetrack with platinum, which we may want for other purposes, in particular to stabilize the chiral domain walls. And then the concept is we would build writing currents formed from spin triplet supercurrents, which we would generate using a variety of structures in which we have these non-collinear spin textures. Perhaps the most interesting is this chiral antiferromagnet with no net magnetization. So we think this is super interesting. And this is something we're currently working on. These are the results on Josephson junctions with platinum. So I think I'm running out of time. We published this in, I think last year or the year before in Nature Nanotechnology. You can read about this. Nature Materials, okay, Nature last, well, I guess 18 months ago. So the diode efficiency is also enormous, even at 2 degrees Kelvin. So we don't need to go to super low temperatures. So I'm going to skip all this and come to the end. So thank you very much for your attention. I briefly discussed some of the work on chiral spin textures on the racetrack, of which we've ourselves have discovered antiskyrmions, elliptical block skyrmions, and fractional skyrmions. Explored various concepts we have to build racetrack memory, both in the 2-dimensional form where we've shrinked the width of the racetracks to below 80 nanometers, which is basically consistent with real world applications. And we've mentioned we have two ways in which we can build 3D racetrack memory. And of course, we're exploring other means of building this racetrack memory. And I mentioned then briefly our work on triplet, the demonstration that we could form triplet supercurrents in a chiral antiferromagnet, here manganese-rich germanium. And I mentioned we found now this Josephson diode effect actually in nickel ditelluride, tungsten ditelluride, platinum ditelluride, and even in platinum. Which is extremely interesting, with up to an 80% difference in the critical currents for current flowing in the left and right directions. And we believe we have a model that can at least account for this phenomenon in these Van der Waals systems. And I briefly mentioned cryogenic racetrack memory, supermint we call it, as a wonderful new form of racetrack that will operate at cryogenic temperatures using these novel phenomena we've recently discovered. Thank you very much for your attention.
Okay. Thank you very much, Stuart. So now we open for questions from the audience. Please raise your hand if you would like to ask a question from Stuart, and I will grade you to the...
Very good.
Let me see. We have 100 and some people, so somebody should have a question. Start with Matthias, I guess, and then we'll start with Roland, and then...
Really super exciting results. You very briefly mentioned about these twisted ribbons, and I found that super interesting. What type of domain walls are there, and what coupling do you envisage between the mechanical twisting and the spin structure?
So the domain walls are basically the same domain walls. It's the same material even as in our conventional racetracks. So these are chiral domain walls.
PMA, nail.
Yes, PMA, nail type walls. In which we use platinum or other heavy metals to create the chirality. So those are very similar, but we see this very interesting phenomenon that just the torsion itself will give rise to new forms of exchange that allow for the difference in motion that we see depending upon the particular domain walls that we use.
Okay, very exciting. Thanks.
Very interesting way of generating new types of domain walls and new forces on them.
Okay, great.
Yeah. So Gambira Sagar, can you please unmute yourself and ask your question? Okay. Yeah, go ahead, Gambira. We don't hear you, but the voice is not on.
Uh-oh.
Now we can hear you. Okay. Oh no, we cannot hear you. No, I still cannot hear you.
Go ahead.
Okay, so let's move on to, and then while you fix your issues, we'll move on to Suman.
Yes, I guess.
Suman, can you please ask your question?
Yes. Thank you. My question is D2D crystal symmetry is sufficient to ensure the antiskyrmion in material, of course, with the strong spin-orbit interaction?
Oh, I didn't get the first part of the question. Maybe Jaro did.
Exactly.
I didn't. Can you repeat it? Your voice was, your sound was a little bit tricky. Can you repeat your question, please?
Yes. Now you can hear me clearly.
Okay. Yes. Speak slowly, please.
Yes. Is D2D crystal symmetry is sufficient to ensure the presence of antiskyrmion in a structure, of course, with in the presence of strong spin-orbit coupling? Is that sufficient condition?
Yeah, you said is the D2D symmetry sufficient to, in the presence of DMI related to spin-orbit coupling, to see antiskyrmions?
Exactly.
Yes,
exactly.
it is. So it turns out the symmetry will determine the nature of the non-collinear spin texture. And there are other materials with D2D symmetry which you can anticipate antiskyrmions. It was predicted theoretically that this system should show an antiskyrmion, which is why we were looking for it.
Okay, I see. Okay. Okay.
What was not predicted was that you could also see these other topological objects, these elliptical block skyrmions that we found, surprisingly, because most, was generally believed that one system has one topological spin texture. It's difficult to create another one. We found, well, we do have one, the first time in one material. And our work has been now confirmed by work from Yoshi Takura's group, where they've actually made exactly the same Heusler compound, manganese 1.4, platinum, palladium tin, and saw both of these objects.
I see. Okay. Thank you. Thank you.
Thank you. Camila, could you try maybe once again to see if you're...
Yep,
yeah, I can hear you. Yeah, we can hear you. Go ahead.
Yeah, thank you for an insightful lecture, Professor. My question was, since it's in the racetrack memories, since it's the presence or absence of the domain walls, which we take as zeros or ones, as the bits, are these domain walls like really clearly defined, or is there any like, since it's just the part where the spin rotates from one direction to another, is there a well-defined boundaries for this domain walls? I thought that would be important because that's what we take as zeros or ones.
Yeah, these are well defined. The domain walls are clearly defined. They have their own properties. They look like small nano objects. They have mass, they have momentum. So it's a well-defined object.
Okay, yeah. That answers my question. Thank you.
Thank you. Revas, can you go ahead and...
It is.
Yes. Yes, thank you very much for this extremely inspiring talk.
Oh, thank you.
But you spoke quite a bit about spin textures and skyrmions in ferromagnets.
Yeah.
What is the situation with antiferromagnets? I don't mean synthetic ones, but real proper nail antiferromagnets.
Yeah, that's a very interesting question. And I think that there hasn't been much work on truly antiferromagnetic systems which show skyrmions, but there's no reason why they should not show skyrmions and other objects. Again, it would depend on the crystal symmetry that would determine the Illusion-Scammino exchange, and that would then can lead to complex spin textures. Probably more difficult to detect than in the case in these systems. If you have no net magnetization, it's more difficult. However, you can have pseudo antiferromagnets where, let's say, you have two sublattices with different elements, let's say in the rare earth transition metal systems, for example, or other systems in which the two
ferromagnets, right?
No, it turns out you can have like a manganese-based antiferromagnet where you have two manganese atoms on two distinct sites, two distinct local.
That's okay.
They can have different properties, and then you could detect those. Very interesting question. But I think synthetic antiferromagnets also, there's been some nice work by Vincent Gross on synthetic antiferromagnets, where I think he's seen maybe not be skyrmions, but textures, objects with chiral walls, which are synthetic antiferromagnets, which is quite nice.
Thank you. Thank you very much.
Thanks, Alberto. Gisela, thank you for joining us, and please ask your question. If you... Yeah, I can hear you, yeah. But it would be nice to see you if you can turn on your camera.
Thanks a lot for this fascinating talk concerning the applicability of this racetrack memory. I think I see several problems arising. The first is, how is there a technique who can prepare for you, or you prepared by yourself, a closed dense racetrack memory where the racetracks have a distance maybe of about 100 nanometer in this 3D sketch?
Oh, 3D, okay, yeah.
So, and if this would be possible, you always said that the current density is relatively high. So if you would run this kind of racetrack continuously with the numbers you showed, it burns in a second, I guess.
No, basically wrong on both counts. One, of course, we have ideas to prepare closely spaced racetracks. So I have a patent that I filed more than whenever in 2020. Well, it was published in 2020. Wait a second, 2000.
Still around.
2002, what, 2004 or something. And the idea would be if you think of a DRAM, the way IBM builds DRAMs, you build a trench with an aspect ratio of more than 100 to 1, 100 times deep as it's wide. And so it turns out on the edges of these trench, you could develop racetrack if you could deposit using atomic layer deposition, for example, or other techniques. So we're actually working on the possibility of building racetracks by atomic layer deposition. We think we're very close to succeeding. And your second question about how close could the racetracks be? Well, of course, we could put them close together. There's no big deal. That would be similar to modern day CMOS, where you have wiring close together. It's the same thing. We just would build a trench or something and fill it with racetrack, or we would otherwise pattern it. So that's no big deal.
And the high current density will also be no
big deal. So of course we operate the current racetracks, which are not on optimized substrates. You can optimize substrates with greater thermal conductivity to allow for more removal of heat, or you put things on the top. There's many ways of doing that, but we already operate these indefinitely, repeatedly applying current pulses in succession, nanosecond current pulses, so very, very high repetition rates, in order to explore exactly what you are discussing. So we've already seen we can, move a single domain wall backwards and forwards. I don't know what the number is, 10 to the 7 times or somewhere it is, or 10 to the 8, but that's not a big deal.
Yeah.
That's not as many pictures as you take in one day, though.
So it turns out these current, also people say current density, the same current density is already used in a magnetoresistive head sensing device, same current densities. And those devices operate for 10 years and
high current
gigahertz speed. So I don't think that's a problem.
Yeah.
I don't regard it as a problem.
I have a lot of experiences concerning ALD. ALD on silicon and with this oxide is easy. But if you want to deposit with your accuracy of less than 1 nanometer with ALD metallic layers, I think maybe you need development for 100 years.
No, we've done it. We've already done it. We can make racetracks with cobalt and nickel layers a few angstroms thick with perpendicular magnetic anisotropy. We can see domain walls move. We've done that. The problem now is, so we don't think it's a big deal. So of course we've done it on horizontal surfaces, but quite frankly,
I have only
be able to do it on vertical too. So I think that's no problem. It's a challenge, of course, major challenge.
No, but you still have 20 years since you've been talking about it, yeah? I want to see it in my laptop now.
I have to say
that you revolutionized us one time. We want a second revolution.
There's an ALD.
We will see.
Been working on it almost since I came here, so the last 6 or 7 years, but now we've achieved it. Didn't take 100 years, it took 6 years. But I agree, it's super difficult, but we believe
it's 100 years in
I will remember you if I'm still alive.
I have to.
That you promised me functional racetrack memory at room temperature, not at low temperature. 6 years, okay.
I think we've achieved all necessary technological requirements. And now it's more a matter of taking the materials we have, the concepts, and building, as you said, a device with multiple racetracks. There's no roadblock. It's all possible, but it just takes a lot of money.
Yeah, but these roadblocks are normally the real blocks. Yeah.
No roadblock. No roadblock. The only roadblock is money, I would say.
I would be happy.
But that's why you're in the Max Planck, Stuart. Yeah? This is
we don't have enough money in Max Planck to do this.
But maybe there are still other questions, or
no, not really. I always
no. Actually, you're the last one, so we're
okay.
He talks about talking. Yes, it was 45 minutes, became an hour of a talk. I knew this. But I knew this way ahead. Typically, that's already. I already calculated ahead of time. Yeah.
These are good questions, Gisela. Thank you very much. But I think we've achieved a great deal.
This is completely true. Yeah.
I think it looks much more exciting than it because all the same questions you're asking piecemeal 20 years ago. Mostly we solved.
Now but then the next question is, when will I have it in the hand? But it's a matter of money. This is the whole point, right? So
Yeah.
All right. So unfortunately, I think we need to wrap it up.
Okay.
People are
Very
leaving.
good.
I like to
Okay.
thank the
Bye-bye.
170 people that
Bye-bye.
have come.
Bye-bye.
I'll stop the
Okay.
stream
Well, if anybody has
now,
any questions, they're welcome to email me.
and then